Hello, back to algorithm strategy class. We will continue to talk about greedy. This is the last part of the greedy videos. Um, in the last videos, we already talked about these 7 points. And in this video, we will talk about the application of greedy techniques for job scheduling with deadlines and also for data compressions. The first one, job scheduling with deadlines. The problem is we have n jobs to be done by a machine, where each job can be completed by the machine in 1 unit time. And each job has their own deadline and also profit. The profit of job I can be obtained by the machine if and only if the job is completed by, so not after, the deadline. The question is which job and in what order the machine should do to get a maximum profit. The mathematical model for job scheduling with deadlines is we want to maximize total profit we have of jobs that are completed before the deadlines. For example, if we have a machine A and there are 4 jobs with their profits and deadlines like this, so job 1 has the profit of 50 and it has to be done in the next 2 hours, let's say. Job 2 has a profit of 10 and it has to be done in the next 1 hour, for example. And each job 1, 2, 3, and 4 can be done by the machine in 1 hour. So let's say we are here now. The first and the third job must be done in the next 2 hours. And then the second and the fourth job must be done in the next 1 hour. So if we use exhaustive search, there are these many possible solutions. This means we do not take any job. Here, from the 4 available jobs, we only take 1 job. And then here, from 4 available jobs, we only take 2 jobs. And we do permutation for it because we want to also know the order we can have. And so on until we take all the jobs. But here, again, the job 1 and 3 must be done in the next 2 hours, and job 2 and 4 must be done in the next 1 hour. We only can take 1 job for 1 hour, so we only can take up to 2 jobs, right? Because there's nothing left after 2 hours, after the next 2 hours. So here we can just consider these possibilities because we cannot, because taking 3 or 4 jobs is not feasible. So we have these many possible solutions like this. So we either take none of the job, we take only one of the job, or we take 2 of the jobs and we check all permutations we can have. So yeah, if we take none of the job, we don't have any profit, but it is feasible. If we take only job 1, it is feasible because it can be done in 1 hour and the deadline is in the next 2 hours. If we take only the second job, then it is feasible because it can be done in 1 hour and the deadline is still in 1 hour. And so on until we only take the fourth job. And then here, if we take the first job and then the second job, we again consider a timeline. We are here now. If we take the first job first, then here we take the first job. It is feasible because its deadline is in the next 2 hours. This is the deadline of the first job. But for the second job, if we take it here, it has passed the deadline. So it is not a feasible solution. So we don't get anything here. So if we take the first and the third job, the first job is done in the next 1 hour. And then we do the third job next, so it is done in the next 2 hours, which is still by the deadlines. So it is feasible and we get 65 profit. 1 and 4 is not feasible because 4 is done after 1 hour and its deadline is in 1 hour. So it's not feasible. And so on until we get all possibilities and we can check the biggest profit we have, which is obviously 80 here. And yeah, we got the solution here. And how about greedy technique? Here we want to take the largest profit. So of course we want to not lose the large jobs with largest profit, right? So we can choose largest profit first and we put it in the slot that is near to its deadline. So the candidate set is what we can choose. We are choosing jobs. So that is the candidate set. But here, other than choosing a job, we also choose a slot. When will we do the job? So there are the set of jobs and also the set of slots time. Next, solution function. How can we know that if we already found the solution? Of course, we check all jobs. If there's no more jobs that can be put in the slot time, then we have done. Selection function, how can we choose a candidate? We always choose job with largest profit. And we always choose slots that is available, but it is near to its deadline. And then feasibility function, we uh, put the job in a slot, but it must not after its deadline. And the objective function, what is our purpose? We want to maximize total profit from the chosen job. So back to the previous example. Here we have 4 jobs. The largest profit we have is the first job, which has 50. And back to the timeline, it has to be done here. The deadline is in the next 2 hours. We can done it in 1 hour, so we can do it here. So we can put it in slot 1 to 2. So it is feasible and we gain total profit of 50. Next, back to the timeline. We already have job 1 for this one. And of course, we will choose the next job with the largest profit, which is of course this one. And this has the deadline of 1. Before 1, we still have a slot here, so we can put job 4 here. So the next one, we can choose job 4, which is feasible because we still have a slot for it, and we put it in the slot, so we have total profit of 80. So slot 0 to 1 and 1 to 2 is already not available. So for job 3, it has been done before 2, but the slot is already full, so it is not feasible. The same with job 2, it must be done before 1, but the slot is not available anymore, so it is not feasible. And we have the solution, which is we do the fourth job first and then the first job. Here we do it in the slot 0, 1, and then here we do it in the slot 1, 2. This is the pseudocode for greedy algorithm to solve job scheduling with deadlines. So here we can have the initialization for the solution set, and then we choose jobs with largest profit first and check um, if we still have a slot for it. We check it from the rightmost before the deadline until the first slot, and so on until we don't have any feasible solution. So in each step, we choose a job with largest profit and check if there is a available slot to be put in the job. So we check for each job, we check each slot. So there is a um, nested loops we have there. If we don't consider the sorting time, because of course we need sorting times to optimize the selection process, we will have time complexity of big O n square. The next one is data compressions. Data compressions itself is a process of compressing the data to minimize memory use. For example, if we have a document containing 100,000 characters, where the frequency of each alphabet occurrence is like this, so A is occur in the document as many as 45,000, so it is 55%, and so on until F is occurs only 500 times, which means 5%. If we use a fixed length code, which is 3 bit to encode each character, we will have 300,000 bit code. So if we want to compress the data, we can assign a small length code to encode character with large frequency. So the more it is occur, then we can have a small length code to encode that character. A Huffman algorithm is an algorithm is known by many people which use greedy technique. So for a document with n different characters, we check the frequency and we initiate entries where each tree containing a single node whose ID is the character it is representing and the label is the character's frequency. And then we find two roots with minimum weight, and then we always form a new tree by adding a new node whose label is the sum of the label of chosen roots, and we add edges between the new node and the two roots such that the new edge become the new root. The new node become a new root of the new tree. For example, back to the previous example, we have A to F with their own frequency. And here we can choose the two lowest label, which is obviously E and F. So we choose them and we create a new node to combine the two nodes. And the label is the sum of the two nodes we chosen before. And here we can choose two roots with the least labels from this one, this one, this one, this one, and this one. And of course, these two is the lowest one, so we choose the two. Again, we combine them and we choose the next two lowest labels for the roots. We have this one and we combine them. We choose the next two lowest labels for the roots and then combine them again until we only have one tree. We already have the Huffman tree for this, but we also need to label the edges. The edges must be labeled by 0 and 1. 0 and 1 can be placed anywhere. In this case, I will place 0 on the top and 1 on the down. And I applied it on all edges. So after we have the complete Huffman tree, Here we have the character A here can be visited from the node, but from the root by visiting this edge, which has 0 label. To B, we can go like this, from root to 1, 0, and 0. For C, it's 0, it's 1, 0, 1. And then for D, it's 1, 1, 0. And for E, it's 1, 1, 1, 0. And for F, it's 1, 1, 1, and 1. After we have the code, we can do the encoding. So if I want to encode the string pad, then B is encoded to 100. This is B. And A is encoded to 0. And the last one, D, is encoded into 110. The next one, if we want to decode the code. So let's say I have this code and I want to decode it. So I will check if 1 is on the code list. It's not. So I check 1, 1, not there also. 1, 1, 1 is not there also. But 1, 1, 1, 1 is F. So I got F here. 0, we have A. So we got A. And 1 here, nothing. 1, 0, none of them. And 1, 0, 1 is C. So we got C here. And the last one, 1 is not there, 1, 1 is not there, 1, 1, 1 is not there, but 1, 1, 1, 0 is E. So we have finished decoding. So if we compare it with the fixed length code like we have before, we can have 300,000 bits, but here if we use Huffman code, we will have only 224,000 bits, which means Huffman code successfully compressed the data by 25%. In each step of Huffman algorithm, we always search two roots with smallest weight to combine them in a new tree. For an alphabet, we need to search the minimum or the smallest weight as many as this, because we need to find two smallest weight, and it is need to be done n minus 1 time, because from n trees we have, we finally got 1 tree. And finding the largest element can be done in big O log n, so that the time complexity of Huffman algorithm is like this. And that's all for the greedy topic for this class. And the next topic we will have is about divide and conquer. Okay, that's all for now. Thank you for watching and see you on the next video.